Yeah, so today we're going to give an overview of the resource supply curves that we use in our long-term planning models. This is a bit of overview of what we're going to talk about today. We'll do a kind of high-level introduction to conceptually what are the supply curves. Wesley will go into some detail into how those supply curves are actually generated and what goes into them. And then we'll basically close out with pointing to where you can find the supply curves, so the data and documentation for them, and talk a little bit about some studies we've done that basically explore how the supply curves interact and impact the results you see from long-term planning models. So to start, what are the supply curves? So for us, the supply curves are essentially estimates of technical potential and the associated costs for available resources for a certain set of technologies. For our focus is primarily on land-based wind, offshore wind, geothermal, and solar photovoltaics, though you could imagine other technologies that might have some applicability, but these are the ones that we're going to kind of mostly focus on for purpose of this presentation and where they have the most detail in the reads modeling that we do. So these data sets include a couple of different features. One of the pieces here is the availability. So this is just a spatial definition of the available area or land that could be used for deployment of these technologies. And with that kind of available land, we translate also to kind of total generating capacity. So we're essentially identifying areas that are open for development. And then once you understand the set of areas that are open, you can also understand the total capacity that could be deployed. Then we have features related to costs, and we split this out into a couple different buckets. We've got the land costs associated with whatever area you're trying to develop or has potential to be developed. Connection costs, which really look at how if you take that site and then you're going to need to build out things like spur lines, interconnection or tie-ins to the substation or transmission lines, and then also potentially network upgrades to get it to load centers. So we've got cost accounting for those based on the location of the site. And then also, capital and operating costs that can vary based on regional factors or even the site composition itself. So we've got those broken out in buckets since it is helpful to basically be able to play around with them and use different factors in different scenarios or understand which of them is driving different cost outcomes. Another piece here is then generation profiles. So for each available site where you could deploy capacity of any of these technologies, we have a lot of detail on the resource availability over time, and I'll talk a little bit more in detail on this in the next slide. And then a final feature here is the land characteristics. So of this available land, we have a large list of data sets that provide information about what that land looks like, what type of land it is, other uses, things like environmental or species, habitat and ranges. So there's a lot of rich description about what that land is that can be used to try to understand where these technologies potentially are being deployed. So here's a kind of schematic or illustration of like what the supply curves essentially look like. So the left is showing some maps for 3 different access cases, and Wesley will talk a bit more in how this is generated, providing more details on kind of like what goes into these different cases. But essentially, these are showing different levels of potential availability based on exclusions related to different siting criteria or stringency. So you can think of this, open access is sort of the most relaxed, where there's probably the most technical potential, and limited has the least. The maps are then just basically depicting how much available capacity you have by location based on these different siting regimes. And so we basically from these supply curves can get spatially where the available land and then thus potential deployable capacity is for the different resources. Associated with that availability is then also the economic features. So the right is showing this kind of same, basically take all these points of available capacity and look at their costs and sort of stack them up from least to highest cost. And that builds out this kind of curve of potentially deployable resources. So the x-axis is showing cumulative deployed capacity. So you start deploying your cheapest resources, and then you can kind of see as you move along the curve, things get more expensive. This is showing levelized cost of electricity or energy as a summary, though we don't actually use it in our REIDS modeling, but it's helpful to give a kind of sense of the cost of these resources. And there's two different levelized costs here. One is showing just kind of the cost based on the site factors. So that includes any regional multipliers or anything specific about configuring that site, including things like economies of scale. And then the solid line is including, the all-in is inclusive of any interconnection costs and things that are specific to that site. So if you have longer spur lines and transmission routing to get to that site, you see those costs increase. So this, when we talk about the supply curves, we're really thinking about this kind of combination of technical potential and then the economics of the available resources that could be built. As I mentioned on the previous slide, then all these potential sites also come with generation profiles. So we know basically where we can build stuff, what it would cost, and what the availability of the resources would be if you built it there. So the data sets that we have that correspond or align with the supply curves include 15 years of hourly resource data that we can basically use and aggregate up into informing decisions in our planning models about the availability of different resources and how we use them to meet load and also resource adequacy requirements and things like that. So that's the high level overview. As promised, stop here, maybe just see if anyone has any initial questions. And if not, I'll turn it over to Wesley to kind of go into a deeper dive on how the supply curves are created. Go ahead, Pratik.
Yeah, thanks, Brian. I was wondering if I heard you right, so if LCOE is not an input into REIDS, and that's what I've seen before, then could you clarify what components of the supply curves are inputs? Is that just the land availability and developable area, and along with capital costs, and then O&M costs, fuel costs, and LCOE is an output? I just wanted to clarify what's an input into REIDS and what's an output.
Yeah, good question, and you summarized it pretty well. So we take the available capacity that gives us kind of, here's the available or potential deployment for technology in different regions. So we aggregate that up to the kind of REIDS region level. We do take cost information. We just take we have the baseline cost assumption, capital costs that come from the ATB, and then we basically get kind of cost adders from the rev side that, say if this site is going to be more expensive, we're going to add to the cost of developing at that site. But that's in terms of kind of in component cost terms. It's just not done as a levelized cost of energy because we don't know yet how the model is going to use the resource, like if it's going to curtail it or not. So we present the LCOE here because it provides a useful context, but we're ultimately using just kind of like the numerator part of that equation, which is just the kind of component costs, including those different kind of pieces that I talked about, like the land costs, the interconnection costs, and then any specific plant or site level costs.
Okay, that sounds good. Thanks.
Yeah. Yeah, thanks for the question.
And you'll get more detail through here. I think maybe one of the key pieces is, that's a specific use case of these supply curves is going into a long-term planning model like REIDS. And we use specific components, not every, there's other parts of the supply curve outputs that you could use. Other users will have different uses for those and pull the pieces relevant for their work. So, I think here, Brian, you want to go to the next slide? We'll go through some of the more detail, and I think it'll make some of this clear. So to create these supply curves, we're using the REV model, which has been developed at at the lab for quite a while, but the idea is that you have a grid of the United States. Within that grid, you could zoom in and say, okay, well, there's roads, or there's buildings, or there's other things, and we have to have certain setbacks away from those. So that gives us, here's what developable area is, and it's going to vary by technology. The technologies modeled are shown here. You can see it's, the REV renewable energy potential model. It has traditionally been developed as a renewable energy model, but expanding into other things, data centers being one of them that's active development. And then moving also into other technologies as well. So go ahead and go to the next slide. So the process for what this looks like, we'll go through the components more, but just kind of give an overall view. You start with the resource data, so whatever your technology is, so it'd be solar insolation, the geothermal would be your underground temperature, et cetera. Wind, you care a lot about wind speed, so you have that resource data. We run it through a system generation model. In this case, we're using SAM, System Advisor Model, because basically everybody who does this stuff, they don't really care about the wind speed or the insulation, they care about the electricity generation out of the system. So this is the step that translates that resource data into a generation profile. So you get actual electricity production. Then we'll pull in plant economics. These are some of the things Brian was talking about. So the cost to develop at a particular location, any regional cost multipliers. So for example, the site's really remote, so you're going to have to pay per diem for construction workers. That's going to increase cost of the construction, or things like it's really high wind loading here. So if you're going to build a PV system, you're going to need bigger bolts so that it doesn't break when it gets really windy. So things like that have locational cost differences, those will get pulled in. And then we have a variety of technical exclusions. We'll walk through these in more detail, but couple all of those to get, here's the total resource potential we start with. You layer on those exclusions, and then we have, here's what you can build now after you've applied all of those exclusions. And then next step, that transmission routing, where you layer on the transmission grid and say, okay, here's a resource site or a location where somebody might want to build something. How far away is it from transmission? How much might it cost to go from that site to the transmission grid? And then finally getting the profiles either at a zonal level or nodal level, depending on what your use case is. So this is now that hourly profile of production to say what it looks like at that location. So that's the overall process. Now we're going to talk through some more of the pieces in greater detail. Just so the goal here is to help you understand what these are, how they're built, so you could understand how to use them and what they might be useful for. So go ahead, next slide. So we start with the resource data sets. So geothermal, care about temperature, pump storage, hydropower. You care a lot about elevation change. And having places where you could build reservoirs that would allow for that elevation change to move water between reservoirs. For solar, bottom left is we're using National Solar Radiation Database, and then wind uses the Wind Toolkit data set, although it's been expanded into other data sets as well to give additional weather information. But the idea is we have all of these data sets are our starting point, and then if you go one more here, Brian, the two wind and solar are different than the geothermal and pump storage in that they're dynamic. So, underground temperatures are pretty static, but the wind speed or solar insolation is changing dynamically, and so those pieces are captured within these data sets. So we'll have many weather years of information that are used to help characterize and understand the resource there. So go ahead and go next slide. So Brian touched on this earlier. So siting there's a lot of uncertainty with siting. We're doing the supply curves in a deterministic way, but because of that uncertainty, we want to help capture that, and we do that through these different siting regimes. So we have 3 siting regimes: open, reference, and limited access, that capture different kind of views or narratives of siting challenges. So the open access siting regime, that's where we are effectively just saying, if there is resource there and there's not a hard limit for excluding it, then we're going to characterize that resource in that supply curve. So this one will only remove places where there's physical barriers, like, there's really steep mountains or protected lands like national parks. Those will be excluded. Everything else, for the most part, is going to be available. Where the reference access, this one now looks at more kind of typical practices for siting. So that means we're going to use best management practices, places where there's where developers aren't developing. It might be technically feasible, but it's really challenging because of protected species in an area or something like that. We're going to take those off limits. And then the limited access regime is one where we're now saying we're applying more restrictions, and places where it looks like it could be challenging to develop, we'll just take them off the table in this one. So this one is intended to be more of it's not going to be an absolute floor. You can envision futures where things are harder than this, but it's kind of a lower bound type approach for representing things. So go ahead and go next slide here. So within those three siting regimes, we're looking at different categories and applying these categories at those different levels of open, reference, and limited siting. So we'll walk through each of these: the defense, aerospace, social, regulatory, environmental, and technical topographic. So go ahead and go one more here. So first, defense and aerospace, and this is how some of these slides are going to look. There's exclusions applied based on open, reference, or limited siting assumptions. So you could see that very first row of this table for airports and heliports. Those are removed. Like we're just saying, you can't develop on top of an airport. And that's now in all the siting regimes. And then for wind, so second row, there is an additional airport setback. It's not applied in the open siting regime because there's not an absolute restriction. You can't do this, and there's going to be some height limits. But developers aren't doing that. It's kind of a best practice just to not build wind turbines right by an airport. So that one's excluded in the reference and limited siting regimes. And then you'll see farther down Department of Defense radar exclusions, and then radar line of sight exclusions. The reference just has the 9-kilometer radar exclusion. The limited has a radar line of sight exclusion, which is more restrictive than just the 9-kilometer exclusion. So this gives a sense of how these things are handled under the different siting regimes. And all of this, that link here at the bottom, is the technical report that documents all of these. So we're not going to go through them, but if it's a kind of thing that, I want to learn more about that, there's citations in there that says, here's the data set that we use to characterize it, if that is something of particular interest. Our goal here is just to give you a flavor of the kind of things that are included when we're deciding what to exclude and what to leave into these supply curves. So let's go to next slide. So social regulatory is the next aspect, where urban regions would be excluded. And then not an urban, if you're just an urban region, you're not necessarily just automatically excluded, but those urban regions tend to have high density of structures and roads, et cetera, that lead to lots of exclusions. So depending on the specific, the open reference or limited siting, more or less of those regions will be excluded. We also, in this one, capture a lot of setbacks. Those setbacks are pulled from ordinances. We'll talk about those in a minute. And we'll have different levels. So for example, here, if you look at the road setbacks, we don't have any setbacks for open. That's just, again, characterizing the land that's available. And then reference, we're using the median values of siting ordinances we've seen. So that's 1.1 times tip height multipliers for wind, 30 meters setback for solar and geothermal. And then in limited, we're using more stringent setbacks, a 2x tip height setback for wind and a 76-meter setback for solar and geothermal. And that then leads to more or less land getting excluded from these. So go ahead and go to the next slide. So these ordinances are captured through looking at actual ordinances. So we're not just making up values. So in 2022, we did a survey of ordinances across the country. It was manual. We just did a new one last year and have updated the ordinance data set that says, okay, for these different types of features, what have we seen in terms of ordinances? So for example, table here on the top right for wind, we see from road, transmission, or rail, there were 587 counties back in 2022 that we found ordinances for. the 50th percentile setback was 1.1 tip height multiplier. So that's what we used for the reference siting scenario. And then a 2x multiplier was the 90th percentile in what we observed across those. And so use that for the limited siting. So those pieces are updated over time as we better understand ordinances, because those are changing. And then the other piece that impacts these is the wind turbines. So the figure on the bottom left, you can see that the size of a wind turbine, for example, is growing. And if these are tip height multipliers, that is then going to impact the setback. You'll see if you have 1.1 tip height multiplier and your turbine's 200 meters tall, the tip height, that's bigger than if it's 150 meters tall, the tip height. And then that then translates into the spatial context for these, the bottom right figure. So the left map is showing Albany County, Wyoming, where there's not as many structures and other pieces where you'd have setbacks. So there's not very many red bubbles there that are showing where the exclusion layers are from these ordinances, versus Erie County, Pennsylvania on the right, where basically the entire county is precluded from development because of these setbacks, because of population density associated with them. So that these ordinances in context with the underlying infrastructure lead to what the land is that's available for development. So let's go next slide. The other piece that we capture with these is there's a lot of sound ordinances in these counties or in states. And so we're also modeling the sound produced by wind turbines. This is when really there are sound ordinances for other technologies, but it really only applies to wind turbines where it's a factor. To model the sound at different distances and understand what a setback might mean in order to comply with that sound ordinance. So that kind of modeling is also captured inside these supply curves. So let's go next slide. So last layer we want to talk about are environmental, technical, and topographic. So this is things like conservation lands for farming, nationally significant ag lands, big game migration corridors, various species protection areas. So we've pulled a whole bunch of these data sets from organizations that track these areas and then use those as additional exclusion layers, again, with stringency varying if you're the open reference or limited siting. So those are also captured in here to represent where it could be really challenging or not allowed to develop wind, solar, geothermal, pump storage, et cetera, projects. So let's go next slide. So all of these are pulled together again to pulling all these different layers together to show what land area is available. So that's what you see on this map. As you zoom in, you can see the roads, you can see the structures. This is just an illustrative example, but you can see that, those setbacks from those to say, here's the remaining land that might be developable for whatever technology you're characterizing in a specific case. So that's ultimately what's going into the supply curves to show what and where things can get built. So let's go next slide here. So Brian mentioned a variety of characterization things. So we have these exclusion layers. So everything we talked about before was things where we say we're going to allow builds here or not. But then we have other things that aren't specific, like, well, that's not me. It doesn't mean you can or can't build here, but we're going to include them as additional characterization layers so that people who are looking at these could get a better view of what's there. So we've got the list of these shown on the table on the right. An example is shown on the left. This is the fair market land value. This is a data layer that we'll use to adjust the costs of developing a different site. So sites that are really near cities or have more expensive land, those will be more expensive than other locations. And then, just to kind of give a flavor for some of these, the kind of things we've done before are look at federal land ownership. So there's X number of megawatt hours or X number of megawatts of solar available in this county. How much of it is on federal land versus private land? So we'll look at those kind of characterizations just to get a sense for things that people might care about. So Bureau of Land Management, for example, might care a lot about federal versus non-federal land. Or a county planner might care a lot about, like, okay, we know we have a lot of federal land in our county. About how much of it is available on private land? So those kind of things could be really valuable. Or another thing we've looked at are things like national land cover data set to say how much of this land is forested land versus shrubland versus farmland, just to get a sense of what types of land the resource is occupying. Okay, so let's go next slide. So the other piece that we capture with this is the transmission. So because you have a resource, you're going to need to connect it to the transmission systems. This map is just showing distance to transmission for locations in the United States. So this could be an important cost driver for a lot of these resources, because if you are producing electricity, you need to get it into the transmission system. So let's go with one more slide here. So we do transmission routing as part of these supply curves, and they follow a lot of the same things that you've seen before. So the figure on the right showing, and start with the exclusion layers. This is the same stuff we were just walking through that we do for the resource. We'll apply those same exclusion layers for transmission that you can or cannot build in these locations because of various protections. You're not going to build a new interstate transmission line through highly protected areas. And then we'll add on to that cost layers. So, we saw the land cost map in a previous slide, but then there'll also be things like the line costs for, how much it costs to build a line, any other risk mitigation costs of like, this is a culturally sensitive protected area, it's going to be more expensive, or terrain cost adders, building a transmission line over a mountain is a lot more expensive than building it through a valley. So those will all get rolled up into a set of cost layers. You couple that exclusion layer with the cost layer to get a cost exclusion layer. And then there's an optional routing friction layer that can be included that would say, okay, well, these kinds of lands we want to avoid, these kind of lands we want to prioritize in terms of moving things through, and those things together would give you a routing layer. And then we'd apply a least cost path algorithm that would say, okay, within this layer, this set of layers, how do we get from point A to point B? And you can see that on the figure on the bottom left. You'd have a wind power plant or geothermal power plant, and have a spur line to get you out to the transmission system, and then maybe some reinforcement to get to a load center or other locations. So you get those kind of things are included in the supply curve and are part of the costs that are reported out of the modeling. So you don't just get, okay, here's a really attractive site, but by the way, it's 200 miles away from the nearest transmission infrastructure. It's going to cost a lot to build it out. So you can get those pieces together and get a better picture of what the resource is and how much it might cost to develop. So let's go one more slide here. So this is showing one view of that. I mean, so you get different siting regimes will give you different costs and different assumptions on those siting and routing layers. We give you different aspects, but this is one output from one scenario where you get different regions have different costs to interconnect those locations into the transmission infrastructure. So that's background on the supply curves themselves, how they're created. I'll pause here. Are any questions before I turn over to Brian to talk more about where you get the supply curves? Okay. Good question. Question is, how frequently are the data updated? So yeah, I mean, I'll answer two ways. One is various data sets that we use are updated at a whole bunch of different cadences. So internally, we're doing updates kind of as things become available, or as we recognize that, oh, this one needs an update, it's getting out of date, but there's a variety of things that lead to individual data set updates under the hood. We produce the supply curves annually, so what you would see on the outside is just an annual supply curve independent of what's going on kind of behind the scenes with various updates and other data sets. So we have been able to annually produce supply curves for some time. We expect to be able to continue to do that going forward. So yeah, the plan is that once a year, new set of supply curves will get released along with documentation for those supply curves. Hey, Brian, you want to take it away here?
Yeah, thanks, Wesley. Okay, I'll talk a little bit about where you can find the supply curve data. So the supply curves are available on the Open Energy Data Initiative Siting Lab page. This is kind of like a clearinghouse for a bunch of the supply curve data. This little animation here is basically showing this viewer that they have on the page. So we're looking at solar PV, and you can see the different sites characterized by the total available capacity. And if you scroll over any of these sites, you get information about the site itself, which I think was supposed to happen, but didn't. So I'll have to update the slide on that. There's also basically at the bottom of the page a bunch of links to the various data sets that you can download. As Wesley mentioned, we publish most of these on an annual basis, so we have the different variants of them available. There's documentation available for the supply curves that get published annually, and then there's also kind of some complementary data sets on things like the ordinances that Wesley mentioned that we also make available as separate data. In addition to that, so we have kind of derivatives of the supply curves that get put into our long-term planning model, namely REEDs. So these are based on the original REV data, but are basically aggregated up for use in our REEDs model. So some of that involves, characterizing the resource at higher spatial resolution to match the zones that we have in REEDs. And then also, taking those hourly capacity factors for the different sites and creating basically weighted average or representative profiles to capture those zones instead of the individual sites. So those, the availability kind of components and the different costs and things like that data can be found directly on the REEDs repo. So there's a inputs supply curve folder, which contains a lot of the useful information with the total available capacity by site and things like that. Because the hourly generation profiles are quite large files, we don't store them in the GitHub repo. Instead, we have them on this other site, Zenodo. So you can download them directly from that site if you want to, just use the profiles for some reason. When you're working with REEDs or running a REEDs run, these are automatically downloaded. So there's parts of the model setup that will go and figure out which of the generation profiles you need for the run you're doing, and collect or automatically download the files from Zenodo and run the model from there. So that's details on the supply curve availability. I'll stop here for questions. I think I see one from Jared. Do you want to go ahead and ask yours?
Yeah, sure, Brian. I think it was just specifically on if a user were to undertake a REEDs run using a particular set of supply curves, is there metadata that goes with that run to indicate which supply curves were used for that particular run that might be useful for users when they're running REEDs as to what data was used as inputs?
Yeah, good question. So we do, I think the answer is yes. There's a couple of different ways we store stuff. There is in that supply curve folder a metadata folder, and that contains some JSON files that have a couple of things like the specifications for the rev run that was used to generate the supply curve. It also has kind of details on the configuration for kind of a submodule called hourlize, and that is what we use to translate the native rev supply curves into the REEDs inputs. So that has a bunch of kind of setting detail that you can find that provide kind of a link between the original data source and the data that's in the repo. And then the last piece I'll mention is there's also in that folder another file called rev paths, which provides links to where the supply curve files that are used in REEDs. It basically points back to the file system where that came from. That last one's probably mostly useful for lab users if they're looking to find the original source of the data, but also kind of provide some tracking of what data set was used. And
Brian, another question here. In terms of how how far can you zoom in on the supply curves? I mean, you showed the map, which was, I think just that one, I think shows it at 11.5 kilometers. But then what if you want to zoom in beyond that? Are there options to do so, or is this the highest resolution available? With this, the background that I don't know that we said, the underlying data sets, many of them are characterized at a 90-meter resolution. So at least the pieces that go into that rev model that's building up these supply curves has native 90-meter. But do you want to talk about any of the, okay, well, this is showing the 11.5 kilometer, which is obviously much bigger than 90-meter. What is, if you want to look sub 11.5 kilometer, are there options for that? Or is it just now aggregations up to 11.5 kilometers?
Yeah. So I pulled up the site again since my video got clipped, but you can sort of zoom in on this and see the individual sites. These are all, correct me if I'm wrong, the 11.5 kilometer resolution. So as far as this map, that's the kind of lowest level you can get. And I think that's probably, for most of the data, the smallest level of resolution. Now, as Wesley mentioned, that's kind of built up from the 90-meter the 90-meter resolution for a lot of the data sets, but then the aggregation to the 11.5 is ultimately what's used to report a lot of things. There are, I think, a couple of the spatial features that maybe have some insight below that. So some of them, for instance, provide like a percent coverage of that 11.5 kilometer grid cell. And so you might have something that says, you know, of that grid cell, 60% of this land is like DoD or federal land or something like that. So to that extent, like maybe you're getting a little bit of like a view of, you know, that pixel being split up. But I think for the most part, the 11.5 kilometer is sort of the lowest you'd be able to kind of see stuff in the data that's published.
And yes, there's a second question. When we say 11.5 kilometer, what we mean by that is an 11.5 by 11.5 kilometer grid cell. So not, yeah, so the total area would be that, you know, 121 kilometer squared space.
Oh yeah, thanks for clarifying that. And then I guess let's circle back to your question, Bryn. I mean, I think the 11.5 by 11.5 does give you, I mean, I think you're able to kind of zoom in here. You know, if we pick these places in, we're zoomed into Kansas here, you know, you can kind of see around that area what's going on. So I think it gives you a pretty good opportunity to, if you're interested in a specific location, to see what's going on in the area around that at the town or city level. Any other questions on data resolution or availability? Okay, cool. I'll talk a little bit then to close here about how these are used in our long-term planning models. So resource availability is a key input to the model, and that's both, there's kind of the two aspects of that, which we've already touched on a bit. Obviously, the temporal availability is really important. So again, going back to those hourly generation profiles, that provides really useful insight to the model when the model is trying to decide, it's making investment decisions between a solar farm or a wind farm or, you know, gas capacity. And if it's trying to meet some sort of load that's occurring in the winter morning, it's going to be able to use this temporal availability to understand, you know, hey, maybe solar is not going to be around because it's still dark out in the winter morning, but wind is. So it's that generation profile with the kind of explicit temporal resolution is a really important feature when the model is basically trying to determine what it needs to build to make sure it can serve load and meet all the resource adequacy requirements for the system. And then the spatial availability is also important here, you know, both from the perspective of figuring out the total available capacity of what you can build. So, you know, the model would maybe love to build a ton of solar, but if there's not available solar, then it's not going to be able to do that. That also kind of interfaces with the cost piece. So when Wesley was mentioning, you might have really great solar or wind sites, But if they're very far from the existing transmission network, they're going to have higher costs. And so you're going to basically make an economic choice between that versus other technologies like gas or nuclear or whatever. So the model is kind of constantly balancing and weighing those trade-offs to make its investment decisions. And there's also, that piece of the transmission is thinking about interconnection and spur line costs, but there's also sort of the higher level interzonal transmission to consider. So you notice in these maps, like you have a lot of, particularly in the limited siting cases, you tend to exclude a lot more on the east because you've got a lot higher density population and structures. And so there's kind of the question of like where you can build stuff and then the transmission you need to build to get it around. So the model across these different siting regimes is to kind of think about where it can build the resources that it wants, and then also what interzonal transmission it might have to build to support those and get that to the load centers. And so it's able to consider the cost of doing all that against other different competing technologies and try to figure out what the optimal is across those choices.
So Brian, just one other piece here I want to flag is that Brian was talking about a lot of like modeling that would capture that full suite of things. But even like I was helping with a utility that was doing an IRP, and they're just like, we want a resource that's far away, that's close, and that's only a little far away. And we were able to use these supply curves to develop those 3 candidate options that they wanted to consider in their IRP. So there's some models that will consider the full suite of resources. There's others that will just say, okay, well, now I have this supply curve. I don't need to represent the entire supply curve, but I could use it to pick representative cases that then we'll give to our model to choose between those 3 resource options. So there's a lot of ways that those could get pulled into a variety of planning activities, but they're pretty foundational for almost any long-term planning exercise, kind of independent of the model that's getting used for that long-term planning.
Yeah, thanks, Wesley. No, I think that's a good point. It's sort of at the core level, if you're just thinking about building a wind and solar site, these would provide a lot of insight into what's available. And then at the higher level, as you go to a model like REEDS, you're taking this data and that's becoming or interacting with a lot of other features. Some of them I already discussed, a couple more to mentioned here, where you've got things like state and regional policies, for instance, to either deploy specific technologies or to meet some sort of emission standard, costs of different technologies that might vary by region, demand growth. So trying to understand different growth in different regions and balancing that with the available resource that you could build. So all those are kind of interacting in a model like REEDS, but the supply curves provide a really foundational data set for making informed trade-offs for those technologies. And we do see that they make a difference. So we've done a couple of studies where we, look at the different siting regimes and run capacity expansion modeling and try to understand the range of possible outcomes and, are able to kind of quantify some of the results. This tends to be a pretty big driver for wind. So the wind supply curve, as you move from that open to limited siting case, really becomes quite restrictive on a lot of the potential wind capacity, and in particular, a lot of the quality wind. So you'll find that the higher siting restrictions will cut down on the amount of total deployed wind in kind of future deployment scenarios. This is from a 2021 study. You can see that the land-based wind capacity varies from, a little bit over 500 gigawatts to just under 200 gigawatts, depending on the kind of nature of that siting restriction. So quite a big difference in how much wind you're building on the system based on sort of what's available to the model. And that part of that influence or the design of your plants can also influence sort of the total availability as well. That has to do with kind of how you're siting the turbines and optimizing the setup of the plant, some of which is kind of captured or baked into the supply curve assumptions as well. This is also true for solar in a bit of a different way. I mean, the solar technical potential is quite large, just because there's a lot of land in the country. And wind turbines have, it's more, you've got to space them out more, and there's more kind of restrictions based on the tip height that Wesley talked about. So even in the limited case, you do kind of end up with a lot of solar. However, I think it's worth noting that these restrictions do still really impact deployment, and they can impact your total system cost. So this is a more recent study that we did that looked at kind of variants of the limited siting case, and also an additional case that had even further restrictions. And again, kind of similar with the wind, you notice that depending on the stringency of the siting exclusions and restrictions, you do end up deploying a different technology mix. So the more restrictive it is, at least for solar, then you see less solar deployment, and you're building other technologies, in this case, mostly a mix of gas and wind, but also sometimes geothermal, to try to balance that out. And that has impacts on your total system costs. Typically, when you apply these restrictions, you're going to have higher costs than the kind of least cost system with no restrictions. But the exact impact can vary depending on not just the amount of restrictions, but also sort of the quality. So one thing that was interesting in this study is that the limited and the restricted PV, there are some scenarios, as we were varying them up and down, where they had similar amounts of total capacity, but different, deployment and costs. And that was in part because, which land was excluded could really make a difference in terms of the quality of the resource that was available to be built. And then one more to flag here is a study we did that kind of introduced her connection to land cover change and tried to explore how that would impact the supply curves as well. So the kind of motivation for this is that these exclusion layers are all, or many of them are connected to development. So as you build out more structures, you're excluding more areas. So over time, we expect development to change. There'll be other changes to land cover use, and so we thought it'd be interesting to try to capture that and then understand how that might impact the deployment in a capacity expansion model. So we took projections of different land cover use changes over time from IPCC scenarios, use that to basically build out these different REV supply curves based on these different futures, and then looked at the changes in deployment of different technologies. And I think one piece that came out of this that was also interesting is you have these trade-offs across the scenarios. So, in some cases, you've got these higher development cases where there's a lot more development that maybe is forcing more PV off the system because there's less available supply curve to develop. On the other hand, you might have the other scenarios where there's more potential for solar deployment because there's less development in certain places. That might mean you get more solar on things like cropland and other land cover types that maybe I don't know, there might be questions about whether you want to use that for solar. However, then when you kind of look back at the net change, those scenarios might have a positive impact. So like maybe you're adding a lot more forested land back because the land cover change overall is less developed, and you're able to see a lot more of the previously developed land returning to forested land, even if you're using kind of more cropland or forested land for things like solar. So anyway, this is just to say that with the kind of detailed REV supply curves that we've been talking about here, we're able to kind of look at these types of scenarios and think about not just land cover use for things like wind and solar, but how they compare to other types of land use, and looking out to the future to understand how that will change over time. So with that, just maybe want to close out here with a few cautions or caveats on using this data. So the supply curves, are pretty highly resolved in a lot of useful detail, but we wouldn't, recommend using them for considering individual projects. I mean, they might be useful in some sense of like a screener tool if you're looking for a whole bunch of sites and want to find some candidates to down select. But ultimately, when you have specific individual projects, there's going to be a lot of siting details that are contingent on that location that we just may not be able to capture in these types of national aggregated data sets. There's also specific things that we know we're not capturing, easements, conditional use permits, zoning requirements, and that list is probably got a few more on there that are pretty important. So the other piece, and we talked a little bit about this, but that 90-meter resolution of the kind of underlying data sets, that is pretty resolved when you look at the whole country, but it does mean that, if you're looking at specific places, you're not necessarily capturing local factors. The other piece is that supply curves are static. So as Wesley mentioned, we do aim to update these annually, but they're always going to lag most recent conditions. And it's not always the case that all the underlying data sets are updated, on that regular basis either. So there's always going to be a little bit of a gap of the published data versus where the conditions might be on the ground. And finally, we're using a lot of really rich data sets, but those themselves, have their own sets of uncertainty in terms of how they collect and assess the spatial lands or spatial features that they're trying to identify. And so we're sort of relying on those data sets, and, all the kind of analysis using those features should kind of continue to think about the underlying caveats of those data sets. So I think that's it for our webinar. A few minutes if there are any remaining questions.
Yeah, and I was question put in the chat about the specific use cases in terms of how they're used. So obviously you've seen some of the modeling exercises, and that's at least the most common way I've seen them used, both within our organization and elsewhere. There's a lot of organizations that use these for doing long-term planning models. They're also used pretty regularly for things like different organizations or parts of the government. So, Fish and Wildlife Service really cares about, we hear about developers, where should we expect interest in our region, and we could show them where the lowest cost sites are through these supply curves are really useful for that kind of thing of, it looks like with this kind of initial screening, this part is, this part of the state or this part of the region is where the lowest cost, closest to transmission sites are. So you'd probably expect more interest there than other places as kind of a starting point. So they get used a lot for that kind of piece, as well as just information of okay, our state has a goal to do X, or a city has a goal to do, we want to get 20% of our energy from solar. Can we do that? And it's just it give that first pass of well, is there enough land to even build that within, or is it we'd have to cover every square foot of land with solar panels? It's well, people aren't going to want that, so maybe we need to rethink what our goal is. So it's really useful in those kind of understanding what's possible, what's available. So that's at least a lot of what we've seen. And then in terms of people using them and getting in trouble with them, at least at the 11.5 kilometer resolution, one of the reasons they're 11.5 kilometers and not at 90 meters is to avoid some of that false precision that comes out if you try to look at well, this 90-meter picture looks like a great place. The 11.5 kilometers makes it kind of aggregates a lot of that up. So it's harder to get in trouble looking at specific pieces. But certainly, just because with the exclusions and assumptions you applied, we say you could deploy something doesn't mean you can. There could be other things going on. You could have a local community or environment that's technology X, we don't want that here. So even though it's technically allowed or feasible, it may not be socially feasible or other pieces like that. And then finally, last question I saw here was, if you want help, how do you get help? There's some connections, or there's some, as you pull down the data sets, there's some contact us places. So if you get stuck with something, you're more than happy or more welcome to reach out, and we'd be happy to respond. So anything you want to add here, Brian, before we close out?
No, I think that covers it.
Cool. Well, thanks everybody. Appreciate the questions, appreciate the engagement here, and look forward to being connected down the road.